browser window now. The screen controls allow you to navigate through the e-learning experience. Using your browser controls may disrupt the normal play of the course. Click the Attachments link to download supplemental information for this course. Click the Notes tab to read a transcript of the narration. At the completion of this course, you should be able to identify main motor starting methods, recognize the frequency converter principle and its advantages, realize substantial energy savings using speed control, reduce harmonic distortion generated by frequency converters, and calculate the payback of an investment in a variable speed drive. Many motors only have two settings, on and off. They operate at constant speed. If a motor turning at constant speed is driving a device or process that requires less output, adjustments are required to achieve the desired output level. This adjustment is often achieved by letting the motor run at full speed while using downstream devices to block part of the output. For fan applications, we have motors generating a full flow of air, and we use dampers to partially block and reduce the flow. For pump applications, we have motors generating a full flow of fluid, and we use dampers to partially block and reduce the flow. Energy is used to generate the output, and then it is immediately thrown away. This is like driving your car by having one foot fully depressing the accelerator pedal and the other on the brake to constantly control the speed. It sounds absurd, but this is still one of the most common control methods. An estimated 60% of motors are not speed controlled. The focus of this course is to explore the different ways we can control motor speed efficiently and with minimal physical stress on equipment. In addition, we'll discuss other advantages such as controlled starting and regulated torque. Many types of equipment can benefit from proper speed control, from pumps and fans to compressors and machines. We'll also talk about energy quality in terms of power factor, and we'll address the issue of harmonic distortion. But first, let's see just how dramatic the financial impact of speed control can be. To do this, there are a few simple physical laws that you need to know. These are called the affinity laws. Flow is the output from a device, such as a fan, pump, or compressor, expressed in cubic meters per second or cubic feet per minute. It is proportional to the shaft speed of the motor. This means that with half the shaft speed, you get half the flow. Pressure is proportional to the shaft speed squared, so with half the shaft speed, you get a quarter of the pressure. Let's say you were getting a pressure of 100 for a shaft speed of 10. For this example, the units of pressure or speed don't matter. 10 squared is 100. Now let's reduce the shaft speed to 5. 5 squared is 25. Half the shaft speed, quarter the pressure. Now is where it gets interesting for us. Power is proportional to the shaft speed cubed. Half the shaft speed uses 1/8 of the power. Let's see that calculation. Imagine you have a shaft speed of 10. 10 cubed is 1,000. 10 times 10 times 10. Now let's take that speed down to 5. 5 cubed is 125. 5 times 5 times 5. Half the shaft speed, 1/8 of the power. So if you have a fan or a pump that doesn't need to run at 100% flow or pressure output, you can reduce the shaft speed and hence the power consumed by the fan. This is an example of an ideal curve of power compared to flow based directly on the affinity law. Note that real devices will have curves that are offset or a different shape, because real devices are not ideal and have varying performance characteristics. A small reduction in speed can result in a much bigger reduction in power consumption that you might intuitively expect. A variable speed drive is more efficient, but there are a number of other benefits to consider. For instance, with variable speed drives, starting and stopping operations are made smooth and perfectly controlled. Slow starting also minimizes inrush currents that often accompany a motor suddenly starting. Inrush currents cause voltage sags that can have damaging effects on the motor and other affected equipment. Variable speed drives are sometimes called variable frequency drives This is because the drive receives AC power at a constant frequency, such as 50 or 60 Hz, and converts it into a variable frequency for supply to the motor. They are found in many applications such as elevators, HVAC systems, pumps, fans, cranes, and conveyors. Let's look at the question of how you start the motor. There are three options associated with starting a motor. They are direct online, star delta, and soft starting. Direct online starting connects the motor's stator windings directly to the mains supply. The motor will start and accelerate according to its natural characteristics. This starting method is suitable for stable supplies, mechanically stiff, and well-designed shaft systems, and it is the most common starting method available on the market. The starting equipment consists of a main contactor, effectively an on-off switch, which is suitable for the required current, and a thermal or electronic overload relay. The disadvantage of a direct online starter is the high inrush current that occurs when the motor starts turning. It may draw a current that is 5 to 7 times the nominal current until it is up to full speed. These inrush currents can generate mechanical shocks that warrant oversized wiring and additional surge protection. Next is the star-delta starting method. This method needs 3 contactors and a control part to manage the contactor sequence. Both ends of the motor windings must be accessible. Motor windings are connected in star formation upon starting. Once the motor torque matches the load torque, the winding connection is changed to delta connection. Star delta provides a softer start than direct online, but acceleration is still not controlled. Star delta is always used for motors above 10 kilowatts to preserve and optimize the electrical installation and mechanical parts. The motor is started with the Y or star connection and accelerated as far as possible, then switched to D or delta connection. Notice how the star-delta connection causes a starting current of about 1/3 the current associated with direct online starting. This rupture in the star-delta starting current is the result of the starting current making the switch between star and delta. Although this starting method is softer, it requires a motor with 2 extremities of wirings connected to the terminals. When starting in star, the motor nominal voltage, the peak of current, and the starting torque are divided by 3. Direct online and star-delta motors are standard. However, at levels of over 10 kilowatts, star-delta has traditionally been more common. At levels over 10 kilowatts, installations and mechanical parts are rarely strong enough to withstand the associated inrush current. Now more than ever, soft starters are used instead of star-delta for levels over 10 kilowatts. Soft starters increase voltage gradually to generate a smooth, steady acceleration and are perfectly compatible with direct online and star-delta motors. Although a soft starter does smoothly and gently start a motor and bring it up to full speed in a controlled manner, it does not provide substantial energy savings or variable speed control. During the starting process, the soft starter progressively increases the motor voltage so that the motor becomes strong enough to accelerate the load to rated speed without causing torque or current peaks. Soft starters can also be used to control the stopping of a process and provide thermal and short-circuit protection for the motor. Let's summarize what we have just learned. Direct starting methods are inexpensive, but they do not perform as well. Direct online and star-delta starting methodologies can be stressful on mechanical parts and gear trains. They also draw high inrush currents. The soft starter preserves the efficiency of gear trains and mechanical parts, but does nothing to master speed or torque, which are the main factors to control in a process to make significant energy savings. We estimate that at least 60% of motors are not speed controlled, so let's discuss the advantages of variable speed drives next. Let's first look at mechanical variable speed drives. The basic concept behind adjustable sheave drives is very similar to the gear-changing arrangement used on many modern bicycles. The speed is varied by adjusting the ratio of the diameter of the drive pulley to the driven pulley. Historically, electrical VSDs, even DC drives, were complex and expensive, and were only used for the most important or difficult applications. So mechanical devices were developed for insertion between a fixed-speed electric drive motor and the shaft of the driven machine. Mechanical variable speed drives are still favored by many engineers for some applications, mainly because of simplicity and low cost. But they are not very efficient and reliable, and the speed range is very limited. Hydraulic VSDs are often favored for conveyor drive applications because of their inherent soft starting capability. In hydraulic systems, the motor or the coupling is managed by oil pressure rather than a magnetic field. It is this pressure regulation and flow control that allows for progressive starting and speed control. Hydraulic drives also tend to be more efficient than electrical ones in systems that require high torque in a small space. They are used in all types of transportation and earth-moving equipment because of their inherently high starting torque. Both of the common types work on the same basic principle, where the prime mover, such as a fixed-speed electric motor or a diesel-petrol engine, drives a hydraulic pump to transfer fluid to a hydraulic motor. The output speed can be adjusted by controlling the fluid flow rate or pressure. The electromagnetic or eddy current coupling is one of the oldest and simplest of the electrically controlled variable speed drives and has been used in industrial applications for over 50 years. In a similar arrangement to hydraulic couplings, eddy current couplings are usually mounted directly onto the flange of a standard squirrel cage induction motor between the motor and the driven load. Using the principles of electromagnetic induction, torque is transferred from a rotating drum mounted onto the shaft of a fixed-speed electric motor across the air gap to an output drum and shaft which is coupled to the driven load. The speed of the output shaft depends on the slip between input and output drums, which is controlled by the magnetic field strength. The Ward-Leonard system comprises a fixed-speed three-phase AC induction motor driving a separately excited DC generator that in turn feeds a variable voltage to a shunt-wound DC motor. So this is essentially a DC variable speed drive, a complex structure that has largely been replaced by electronic devices. Since the 1970s, the controlled DC voltage required for DC motor speed control has been more easily produced from the three-phase AC supply using a static power electronic AC-DC converter, or sometimes called a controlled rectifier. Because of its low cost and low maintenance, this type of system has completely superseded the Ward-Leonard system. However, DC motors are less common now due to technology and maintenance cost. In the case of an AC to AC frequency converter, the mains AC supply voltage is converted into a DC voltage and current through a rectifier. The DC voltage and current are filtered to smooth out the peaks before being fed into an inverter, where they are converted into a variable AC voltage and frequency. The motor supply is controlled so that the ratio between voltage and frequency remains constant. This allows an AC motor to provide its rated torque up to its rated speed. The variable speed drive is also known as a frequency converter and is known for having very accurate speed and torque regulation. It has a rectifier bridge followed by an inverter. Both allow voltage amplitude and frequency to be varied. The input rectifier converts the three-phase network supply to DC. The DC voltage that is obtained is then filtered. From this DC supply, an inverter rebuilds an AC supply to feed the motor. Here we see a table comparing different starting methods. As you can see, variable speed drives not only yield better performance, but have lower operating costs as well. You may download this information from the attachments link and downloading the document called Starting Methods Compared. Variable speed control has many advantages compared to older technologies. Let's very briefly look at these advantages and some of their applications. For a bottle conveyor, the aim is to not break the bottles when the conveyor starts or stops. A speed drive here will allow for customized speed ramps in order to accelerate and decelerate the conveyor without shaking the bottles. Load control is important in large installations, but so are peak current and mechanical shock limitations. Variable speed drives allow electrical and mechanical equipment to be downsized by limiting the starting current. For passenger lifts, movements must not be abrupt and perfect positioning is required independent of load. A variable speed drive is the most suitable solution to control speed and positioning. The variable speed drive also ensures braking control, which is synchronized to the movement. Providing a device with the best adapted power characteristics preserves mechanical parts. An escalator with frequent starts and stops tends to stress mechanics. An electric speed drive ensures acceleration and deceleration while limiting jerks that can accompany high torque applications. VSDs feature a user interface for monitoring, diagnostics, and control. An LCD screen and pull-down menu replace the old buttons and potentiometers. Drives are also communicating devices. They can be managed by a controller using one of the many field bus protocols available on the market. Speed control can also contribute to energy savings. For pump and fan installations, this savings can be upwards of 70%. In this fan installation, observe the power consumption versus airflow curve. Every device will have its own characteristic curve for power versus flow. They may not look like the ideal curve that we saw when we looked at the affinity laws due to the design of the specific device. The red line is the power versus airflow curve when the airflow is controlled with a damper. For 80% airflow, the motor is operating at almost 100% of its power. If the damper is replaced by a variable speed drive, airflow information is used to adjust the motor to the right speed. When the fan speed varies, power increases proportionally to the square of airflow. For 80% airflow, the motor operates at only 50% of its power. This means power consumption is halved by the use of a variable speed drive compared to a damper solution. How is energy wasted in water distribution? Let's look at an example. In a distribution system, water is moved by a pump. In this simplified irrigation installation, the pump is powered directly by an AC supply and always runs at full speed whatever the demand. A valve opens and closes to vary the flow. Reducing the flow using a valve causes what are called load losses. As the valve slows the flow of water, a large part of the power is lost. Providing 80% of the flow causes the pump to consume 80% of the power. Providing 50% of the flow causes the pump to consume 65% of the power. Remember the affinity laws we saw at the beginning of this course? Power is proportional to shaft speed cubed. Although this is an irrigation example, the same principle applies to other pumping systems. How can we save up to 50% of the energy in water distribution? Let's replace the direct online starting with a variable speed drive. The valve is no longer needed, since the flow can now be adjusted by the variable speed control of the pump. To vary the flow, the speed reference is adjusted. The difference between the green curve and the red curve represents the energy savings. Providing 80% of the flow, the pump only consumes 50% of the power rather than 80%. Providing 50% of the flow, the pump only consumes 20% of the power rather than 65%. Depending on the operating cycle and the average flow, the variable speed drive can create energy savings of 20 to 50% on a pumping system. The same is true for ventilation systems. In fact, using speed drives in fan installations brings 20 to 70% in energy savings. Notice the power consumption versus airflow curve in this fan installation. The blue line is the power versus airflow curve when the airflow is controlled with an outlet damper. The red line is the power versus airflow curve when the airflow is controlled with an inlet vane. The green line shows the power drawn by removing or fully opening the damper and controlling the speed. Using an output damper to reduce the flow to 80% uses 95% of the motor's power. Using an inlet vane to reduce the flow to 80% still uses 70% of the motor's power. And using a speed drive uses only 50% of the motor's power. A variable speed drive is always more efficient than control using a damper. The question is, will it be efficient enough to justify the cost? Devices that only run for a few hours per year may consume little electricity even if they are inefficient. In this case, the gains from a variable speed drive would not be enough to justify the cost of the project. Sometimes if the motor driving the device is very old and close to end of life and is oversized for the application, it may make more sense to replace it with one which is suitably sized for the purpose. This is especially true if the application uses constant speed. The motor can be sized for the correct speed, and any dampers used for control can be left fully open. If variable speed is required, a new motor and appropriate variable speed drive might be the best solution. Commonly, introducing a variable speed drive is a better solution than buying a new pump or fan. It is normally less expensive, more flexible, and can bring energy savings of 20 to 50% compared to the savings from changing an inefficient pump or fan, which tend to be less than 10%. Note that for constant speed applications, adjustments to pumps such as trimming or replacing impellers or changing pulley sizes on fans may bring significant energy savings and pay for themselves quickly. These adjustments can take anything from a day to a week or more to carry out depending on the situation. In many cases, a VSD can be installed in a few hours. If in doubt, a VSD provides the best flexibility since it allows for future speed changes and can be integrated with a minimum of disruption. Whether the motor is old or new, if the damper is normally set fully open, the fan or pump will be running at its nominal efficiency. A variable speed drive's advantage lies in its ability to operate the motor at a different rate. If the damper is hardly used, the variable speed drive will rarely run the fan or pump at a slower rate and will therefore have little effect. If energy happens to be very cheap, then even if the variable speed drive saves a great deal of energy, the saved units may translate into only a small amount of money saved. Compared to the cost of the project, this may not be enough to justify the purchase. Local pricing of the project will also affect the feasibility. If the equipment cost is high, then a project that might be feasible in one country may not be in another. Have different expectations of payback. Some customers may be satisfied by a 5-year payback to 50% on a pumping system. The same is true for ventilation systems. In fact, using speed drives in fan installations brings 20 to 70% in energy savings. Notice the power consumption versus airflow curve in this fan installation. The blue line is the power versus airflow curve when the airflow is controlled with an outlet damper. The red line is the power versus airflow curve when the airflow is controlled with an inlet vane. The green line shows the power drawn by removing or fully opening the damper and controlling the speed. Using an output damper to reduce the flow to 80% uses 95% of the motor's power. Using an inlet vane to reduce the flow to 80% still uses 70% of the motor's power. And using a speed drive uses only 50% of the motor's power. A variable speed drive is always more efficient than control using a damper. The question is, will it be efficient enough to justify the cost? Devices that only run for a few hours per year may consume little electricity even if they are inefficient. In this case, the gains from a variable speed drive would not be enough to justify the cost of the project. Sometimes if the motor driving the device is very old and close to end of life and is oversized for the application, it may make more sense to replace it with one which is suitably sized for the purpose. This is especially true if the application uses constant speed. The motor can be sized for the correct speed, and any dampers used for control can be left fully open. If variable speed is required, A new motor and appropriate variable speed drive might be the best solution. Commonly, introducing a variable speed drive is a better solution than buying a new pump or fan. It is normally less expensive, more flexible, and can bring energy savings of 20 to 50% compared to the savings from changing an inefficient pump or fan, which tend to be less than 10%. Note that for constant speed applications, adjustments to pumps such as trimming or replacing impellers or changing pulley sizes on fans may bring significant energy savings and pay for themselves quickly. These adjustments can take anything from a day to a week or more to carry out depending on the situation. In many cases, a VSD can be installed in a few hours. If in doubt, a VSD provides the best flexibility since it allows for future speed changes and can be integrated with a minimum of disruption. Whether the motor is old or new, if the damper is normally set fully open, the fan or pump will be running at its nominal efficiency. A variable speed drive's advantage lies in its ability to operate the motor at a different rate. If the damper is hardly used, the variable speed drive will rarely run the fan or pump at a slower rate and will therefore have little effect. If energy happens to be very cheap, then even if the variable speed drive saves a great deal of energy, the saved units may translate into only a small amount of money saved. Compared to the cost of the project, this may not be enough to justify the purchase. Local pricing of the project will also affect the feasibility. If the equipment cost is high, then a project that might be feasible in one country may not be in another. Customers have different expectations of payback. Some customers may be satisfied by a 5-year payback, while others may require 3 years, 2 years, or even as little as 1 year. A variable speed drive generally pays for itself within 1 to 2.5 years. Let's look at a short example of these economic factors. Imagine you have a motor that is nominally rated at 50 horsepower. That would be roughly 35 kilowatts. This motor runs 12 hours per day, 5 days per week, 50 weeks per year. So the annual consumption will be about 105,000 kilowatt hours per year. Let's imagine that you have assessed the fan powered by the motor and determined that if you remove the outlet damper, the power needs will be reduced by 30%. If energy costs 0.1 euro per kilowatt hour, the annual energy savings of the installation are 3,150 euro per year. If the speed drive installation costs less than 3,150 euro, it will pay for itself in less than 1 year. However, if the cost of energy is only 0.05 euro per kilowatt hour, then the savings would be only 1,575 euro. Depending on the price of the drive, this project may no longer meet your investment criteria. If the motor is much smaller, or the operating hours are fewer, these will also impact the savings. Estimating your savings requires you to know your current energy costs, operating hours for the equipment, and the power reduction resulting from changing to variable speed. You may need to consult the specifications of the fan, pump, or other equipment to determine the effect on the power used. With variable frequency drives, energy savings of up to 70% are achievable depending on the type of installation. The highest potential energy savings can be found on pumps, fans, and compressors. To help understand potential energy savings, a couple of new tools are available. The Energy Consumption Simulator compares a conventional fan application using a mechanical control to a variable speed drive to control airflow. You control the level of flow by turning the wheel on the throttle and the variable drive to control the airflow. The simulator then illustrates energy consumption for both options. Another tool is the ECO2 Energy Calculator. This calculator helps identify the estimated return on investment for a variable speed drive within pump and fan applications. Download and install this calculator to build a customized report to illustrate energy consumption with or without a drive, the reduction in carbon footprint, and potential payback period for specific applications. This calculator features adjustable variables to evaluate how duty cycle rebates, installation costs, energy costs, and other variables change ROI. Frequency converters have many advantages, but one main disadvantage is that they generate harmonic distortion in the power network. Let's see with more details what are the problems and the solutions. Harmonic currents and voltages are generated by nonlinear loads connected to the power distribution system. Variable speed drives are themselves nonlinear loads and therefore increase voltage distortion by injecting harmonic currents into the main supply. Instead of a smooth sinusoidal wave, the waveform starts to be a less regular, more distorted shape. If harmonic distortion increases, it can cause problems. These problems can cause protection devices to trip and cut off the electricity to some machines, which disrupts production and causes a nuisance. If harmonic distortion increases above a certain standardized level, it becomes a form of pollution that can cause problems. You can learn more about this in our class on power factor and harmonics. Harmonics can overload the rectifier bridge and drive capacitors. Consequently, both users and nonlinear load manufacturers limit them in order to guarantee the quality of the energy of the network. Harmonics reduction can be achieved either by structural modifications in the drive system, installation design, or by using external filters. Total harmonic distortion of current, or THDI, is a measure of the impact of harmonics on the waveform. A frequency converter with no filter generates a THDI above 100%. This is not acceptable if speed drives represent a large portion of the installed equipment. Filters are commonly embedded within the drive or connected externally to mitigate harmonics at the speed drive level. They work by eliminating some or all of the harmonic frequencies. A choke is a reactor installed on the line supply or in the DC bus. It smooths the shape of the input current to reduce THDI to about 40%. It is a popular option because of its simplicity and cost-effectiveness. Passive filters are more effective, but also more costly and bulky. A passive filter is constructed from capacitors and chokes tuned to eliminate harmonics of a particular frequency or a few frequencies. Passive filters are generally reserved for power levels under 100 kilowatts and have the ability to reduce THDI to approximately 10%. C-less drive technology uses a frequency converter with very low capacitance values on the DC supply. This is because capacitance is the main source of distortion. However, reducing the capacitance also reduces the performance of the motor control, which makes it suitable for applications such as HVAC, where high-performance speed drives are not required. THDI can be reduced to 30%. A 12 pulses system is a type of drive design that uses two rectifier bridges to supply the DC bus. Each rectifier is supplied by a secondary winding of a specific transformer. Each secondary has a dephasing of 30 degrees. The result on the other side is an attenuation of the 5th and 7th orders of harmonics. An 18 pulses drive involves the same principle, but with 3 rectifier bridges. There are two main types of active filters. First is the active front end, or AFE. Here the classical rectifier bridge is replaced by an inverter controlled in order to draw sinusoidal current onto the network. A line active filter is a device installed on the power distribution network that senses harmonics and injects in opposite phase a balancing harmonic to maintain a sinusoidal line current. They are very effective, but can be expensive. They are normally used above 100 kilowatts and can reduce THDI to under 5%. This chart demonstrates the cost versus efficiency of each type of harmonic mitigation technique. The y-axis indicates the contribution of the cost of mitigation to the cost of the drive expressed as a percentage, and the number above each of the bars is the corresponding THDI rating. The cost of the drive without harmonic mitigation is given as 100%. If the cost of mitigation is 50% of the cost of the drive, the y-axis will show 150%. For the industrial sector, there are no standard total harmonic distortion limits for variable speed drives because it is not possible to know the impact a drive will have on the complete installation without knowing many other things such as the architecture, the loads, and so on. However, some industry segments are more focused on harmonics mitigation than others and require compliance with IEEE or IEC standard guidelines. These standard guidelines address the harmonic distortion at distribution system level. The most effective solution is to study the complete installation, which often leads to a compromise solution, mixing chokes at the level of the drives, separating linear and nonlinear loads in the architecture, and applying a network-wide solution for passive or active filtering. However, for customers who don't know exactly how their installation may evolve in the future, a more comfortable solution may be to use clean drives with local passive or active filters. Unfortunately, using this approach, the cost is quickly doubled. So how do we optimize a power drive system? You could improve the combination of the motor and gears. This would save between 5 and 10%. A much greater opportunity, however, is to consider a variable speed drive. Variable speed control can yield savings of 20 to 70%. When we think of saving energy in the area of lighting, we naturally think of the new generation of energy-efficient bulbs. After all, they reduce consumption by around 80%. If we did for motors what we now do for lighting, we would capitalize on the savings of up to 70% associated with variable speed drive implementation. Now, let's summarize some of the information we have covered throughout the course. Many types of equipment can benefit from proper speed control, from pumps and fans to compressors and other machines. Due to associated costs, traditional direct online starting is the most common starting method on the market today. There are many compelling reasons to consider other starting options, however. These include benefits such as smooth starting and stopping, minimized inrush currents, and electrical efficiency. While soft starters avoid the mechanical stress associated with direct online starting, nothing enables mastery of torque and speed the way variable speed drives do. Despite all the advantages of variable speed drives, at least 60% of all motors are still not speed controlled. For pumping systems, a variable speed drive can save 20 to 50% depending on the operating cycle and average flow. Applying variable speed drives to ventilation systems creates 20 to 70% in energy savings. In fact, a variable speed drive generally pays for itself in 1 to 2.5 years. If dampers are fixed and air or water flow rarely needs to change, it will be difficult to justify investment in a variable speed drive. A VSD's advantage lies in its ability to operate the motor at varying rates. Variable speed drives are nonlinear loads and can therefore create harmonic distortion. Harmonics can overload the rectifier bridge and drive capacitors. As a result, filters are often embedded within the drive or connected externally in order to mitigate the damage harmonics can cause. The construction, cost, and effectiveness of harmonics mitigating equipment can vary. Harmonic filtering effectiveness is expressed in terms of THDI rating. The savings associated with variable speed drives is as dramatic as upgrading to new generation lighting. Speed control savings are ready to be realized. Using tools such as Schneider Electric's Energy Consumption Simulator and the ECO2 Energy Calculator can quantify those savings before any investments are made. Thank you for participating in this course.